Hey, good morning, ladies and gentlemen, or good afternoon. If you're watching this video, I am taking the personal day today because my wife had to go into for knee surgery yesterday. I'm still in the hospital in recovery and doing physical therapy. So I'm going to give you this recording on types of forces. This week is week 5. All right, so if you were to look at week 5, let's take a quick peek at what we're talking about today. We're talking about the types of forces. What is a force? The 10 different types of forces and fundamental forces. Why are we doing this? To describe what a force is, to explain different types of forces, and how they are created, and how they can be used. And why this is important is to better understand the motion of objects. So this continues on our um, introduction to physics and motion. All right, so forces are a push or pull acting on an object. It's a vector quantity, so it has magnitude and direction. And there are two different types. There's contact versus non-contact forces. Contact forces, direct touching. All right, sometimes we call that applied force, a force that we've applied or touched. And there's non-contact forces called field forces and can act as at a distance like gravity or magnetism. Let me show you this video quickly about these types of forces.
Hi everyone, welcome back to High School Science 101. Today we are going into physics and we're looking at forces. And I'm going to explain and demonstrate a few different types of forces for you. Let's get started. A force is basically an interaction that causes an object to start moving or speed up, stop moving or slow down, change direction, or change shape. This interaction can be in the form of a push, a pull, or a twist. We can classify forces into two main groups, contact or non-contact forces. As the name implies, contact forces require physical contact between two surfaces. For example, I'm applying physical force to this putty so I can change it into different shapes. There is physical contact between the source of the force, my hand, and the putty. So therefore, this is a contact force because there is physical contact between the two surfaces. Another great example of a contact force or a byproduct of contact forces is friction. And I would recommend watching my video on that because it covers it in a lot more detail and also gives you some examples on how to increase and decrease friction. Earlier, I said that there were two main groups of forces, contact forces, which I've just shown you, and non-contact forces. So let's take a look at a couple of those. The first one I'm going to talk about is magnetism. Magnets don't have to physically touch each other for them to affect each other. So therefore, magnetism is a non-contact force. In this example, and in fact any example of non-contact forces, there's an invisible field around the object, and the non-contact force will act on any other object that enters that force field. So you can think of this force field as the range of the non-contact force. If something is outside of that field, outside of that range, then the non-contact force won't be able to act on it. A question that I get asked a lot is why are some things magnetic and some things not magnetic? And I can give a very, very simplified answer to this. Everything around us is made up of these tiny building blocks called atoms. And inside an atom, you have a positively charged particle called a proton, a neutral one called a neutron, and they are stuck together in the middle of an atom in the nucleus. And flying around the nucleus, you have these negative particles called electrons. In the atoms of most things around us, these electrons are flying around the nuclei fairly randomly, and overall the object doesn't have a charge. However, in some things, specifically things made of iron, nickel, or cobalt, all these electrons fly around the nuclei in the same direction, and this creates an invisible magnetic force field and makes the object magnetic. Additionally, every magnet has two different ends, a north pole and a south pole. If you try and put two poles of the same type together, like two north poles or two south poles, they will not attract each other. In fact, they'll try and push each other away and repel each other. On the other hand, if you put two different poles near each other, a north pole and a south pole, they will attract each other. Another example of a non-contact force is static electricity, and you might have noticed this when you've touched something metal and you feel a bit of a shock from it. To explain how this one works, we need to talk about electrons again, and just a reminder that electrons are the negatively charged particles within atoms. When we rub two objects together, sometimes the electrons from one object jump across to the other one, and so the object losing electrons, losing negativity, becomes positive, and the one gaining electrons becomes negatively charged. And so these two objects then are attracted to each other because one's positive and one's negative. Sometimes other objects will become attracted to these things that have charges. For example, if I rub a cloth against a balloon, the electrons will transfer from the cloth to the balloon, so the cloth becomes positively charged because it's lost these negative electrons, and the balloon becomes negatively charged. And now if we hold the balloon up to some things, they'll be attracted to it because it has this negative charge. The last non-contact force that I'm going to talk about is the one that affects you every single day without you even realizing it, and that's gravity. When you think of gravity, you probably think of space and planets and moons and stars, but according to Isaac Newton's universal law of gravitation, anything that has a mass has a gravitational field. So for example, there's a gravitational pull between yourself and the computer in front of you, but you don't notice it because it's so small that it's barely measurable. We do notice it when we look at bigger masses, because the bigger the mass, the more gravitational pull it has. And so that's why we tend to really associate it with planets and moons and stars, because those masses are much, much bigger. It's not only the masses of two objects that affects how much they'll be gravitationally attracted to each other, but also the distance between them. And in fact, the distance between two objects has a stronger impact on whether they'll be attracted to each other than their masses. The bigger the distance between them, the weaker the gravitational field. That's it for today. I've covered briefly what a force is and also some different types of forces. When we cover this topic, I also talk about balanced and unbalanced forces, but I might leave that for a video later on.
Okay, so basically what we've talked about today: forces, push or pull acting on an object. It's a vector quantity, both has magnitude and direction. Contact forces and non-contact forces. So we've talked mostly about non-contact forces, which are field forces, can act at a distance, gravity, magnetism, and electrostatic. So types of forces. We've talked about gravitational, electromagnetic forces. We haven't talked about the weak or strong forces in the nuclear inside the atom, but we will a little later. So there are applied forces, frictional forces, centripetal forces, tension forces, normal forces, and many more. So an applied force applied directly to an object by a person or another object. Example, a physical push or pull directly on an object, and object hitting another object. So gravitational force is gravity that acts between objects in the universe. The strength of the force depends on the masses and the objects and the distance from each other. The greater the mass, the greater gravitational force. less distance between them, the greater gravitational force. So gravitational force is equal to the mass times acceleration due to gravity. So force, F, is equal to m, the mass, times gravity. And gravity has this acceleration constant, 9.8 meters per second squared. And we get this unit of N, or newtons. So 1 Newton is equal to 1 kilogram times meters per second squared. So that is our unit for weight. So what's the difference between mass and weight? So let's take a quick peek at another video that will kind of have a little bit better visuals for us. Go here. Okay. So if you take a look at this assignment here, this is our frame of learning. So I'm going to look at this mass versus weight and the normal forces, 5 minutes. Much better demonstrations than I have. So let's take a quick peek of that.
Professor Dave here. Let's learn the difference between mass and weight.
He knows a lot about the science stuff. Professor Dave explains.
Most people are familiar with the term mass and weight, and might assume that mass is simply a fancy word for weight. In actuality, this is not the case, and the two terms have rather different meanings. To put it simply, mass is a scalar, and weight is a vector. This means that mass has only magnitude, since it is a measure of an object's inertia, or essentially how much matter is present within the object. Weight, on the other hand, has magnitude, but also direction, because it is a force, specifically the force that is exerted on an object by virtue of its position in a gravitational field. We will learn more about gravity later, but for now, we can just operate under the common understanding that gravity is a force that pulls things towards Earth. Mass and weight are related in that they are proportional, and objects with more mass will weigh more than objects with less mass. But they are not the same thing, and when we discuss our weight in common parlance, we are actually referring to our mass. Weight can be calculated using Newton's second law, or F equals ma. Take an object like a 100 kilogram person. This value represents the mass of the person, which is more or less constant, barring any huge changes in diet, as it is a measure of the amount of matter in the person. But the weight of the person will depend on their location. On the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared, so their weight will be 980 newtons. On the Moon, acceleration due to gravity is about 1/6 of that of Earth's, because the Moon is much less massive, so the person will weigh considerably less as well. In the vacuum of space, far away from any massive object, the person will be essentially weightless, since there will be no appreciable acceleration due to gravity. In all of these cases, the mass of the person does not change, but their weight will vary depending on the presence and strength of a gravitational field. Since weight is a force, we will have to include weight in any free body diagram representing objects on Earth. This will be a vector with magnitude equal to m times g, pointing straight down towards the center of the Earth, where g represents the local acceleration due to gravity. We learned from Newton's third law that any force has an equal and opposite force, and so we will often encounter something called the normal force. The normal force is exerted by whatever surface the object sits on, and it points in the direction that is perpendicular to the surface. If this is a flat horizontal surface, the normal force will be straight up, opposite in direction to the object's weight. The more mass an object contains, the greater its weight, and the greater the opposing normal force. If these are the only two forces acting on the object, they will be equal and the object will remain at rest. Now that we understand the distinction between mass and weight, as well as the way that weight will be depicted in free body diagrams, we are ready to look at other forces that can act upon objects. Let's check comprehension.
So an object on Earth, its gravity or acceleration due to gravity is 9.8 meters per second squared, has the weight of 62 newtons. What's the mass of this object? Okay, so let's take a quick peek of this. I don't have anything I can write on right now. So the mass of the object on Earth, right, you're going to take, let's just have him show this. So taking 62 newtons divided by 9.8 meters per second squared, we get 6.3 kilograms.
Thanks for watching, guys. Subscribe to my channel for more tutorials.
All right, let's continue on here. Okay, so he helped answer the question, what's the difference between mass and weight? So mass, you think about an object here. So if I draw a block here, so let's say these are the individual particles that are inside here. And the more massive the object, the more particles or closer they're together, more tightly packed they are. That's the way I like to think about those. So I'm putting these dots in here so there's some space between them. Okay, so mass does not change, right? So here on Earth, as we said before, 100, let's do this again. He said, he's talking about 100 kilograms, 100 kilograms was the mass. So that is a representation of that container times 9.8 meters per second, hit the up arrow on 6 squared, gives us 980 newtons. Okay, so that is what we look at. The mass does not change, right? But depending on where you are in gravitational field. So if you were free falling from a plane, then you could be weightless, but your mass is going to stay the same. You feel that effect when you are in an elevator, a fast moving elevator. As you go up, we were to this 100 kilograms moving upward, right? Quickly, you will feel heavier, slightly. If you were to put your foot on a scale, you would feel heavier because not only have you the 9.8 meters per second squared, but you're moving up as an additional acceleration, and you will feel heavier. If you are falling or going quickly down, you'll feel lighter. So people have done this experiment in a fast moving elevator with a scale, and you can see the difference. Now the particles, the only way to get the mass to change is if you were to take some of the mass away. And again, that's like losing weight for us. All right, so go to this next one here. So mass versus weight. Mass is the measure of how much matter an object contains. Weight is the measure of the gravitational force pulling on an object. All right, questions. Which of these properties can change if you go to another planet? Okay, so the weight can change, but the mass cannot change, right? So the mass will stay the same. It's just that the weight changes because of the gravitational force. Because of the gravitational force. Okay. All right, so we're going to stop right there because that's about 20 minutes. And we'll talk again on Wednesday. So Wednesday, I will see you guys later. I'm going to bring my wife back from the hospital today and get her all situated at home. All right, for her recovery. Thanks for you guys. I love you guys. Sorry I missed you. I will see you tomorrow.